thanks everyone for coming, and thanks to Greg for inviting me. So this title was, I submitted this title more than 6 months ago. And I just needed to put all the right words in and figure out what I'm going to talk about the night before. So that was the general idea. So I knew I will have something by the time.
Because things are so dynamic and changing.
Yes, exactly. And that's like our field, right? So I go for vacation for 3 weeks, I come back, and I'm outdated, right? But then I go back and read a paper from 50 years ago, actually it all makes sense, and says, oh, it's just like it was invented yesterday. And that's been my experience all along through my 20-plus years of working in the field and working in different areas of the field. We'll talk about that in a little bit. So I want to give you an example of just that. So this was Douglas Engelbart. Back in 2007 or 8, I called him up and I said, I read this paper, Augmenting Human Intellect. So everybody knows about Douglas Engelbart as the inventor of the mouse, the computer mouse. But nobody knows, or most people do not know, he wrote this paper back in 1962 called Augmenting Human Intellect. So I accidentally bumped into this old paper that was typewritten, and actually somebody had scanned it and put it somewhere on the internet. And it was 7 p.m. at work. I was sitting at work, and it's like, I read this paper. And I read it. It was almost written like it was written for me and the day before. Because back in 2007, everybody was talking about crowdsourcing. Crowdsourcing was the hottest thing. Mechanical Turk, all those things were the hottest thing. So how do you bring intelligence from human beings, who are trained to do things, and combine that with machine learning at that time, what we call AI today, right? So I called him up and I said, Doug, I want you to come up and give a talk. And I'm from eBay, and I read your paper, and it sounds so fascinating, and it's very useful for us. So you should come and talk about it. And guess what he said? The first thing he said was, what is eBay? He had no idea about the company, not that he cared. And then it was supposed to be, I got 10 minutes to talk with him through his secretary, and I landed up talking for 2.5 hours. He was deliberate. He asked me a lot of questions. And I said, what can I talk about? What does eBay do? What do people do? How will the audience find me interesting? I said, don't worry about it. If you remember this paper, just come and talk about the paper, and everybody will identify with the topic on the paper. And I said, by the way, when you come along, bring that mouse with you. So this picture here is the mouse he modeled, and just bring it along. And he said, really, will people be interested in my mouse? I said, absolutely, yes. And then I asked him if it was insured. So he said, do you think it's worth a lot? So I said, I work for eBay. I know the value of these things. So long story short, he came and he was supposed to speak for 30 minutes. He landed up talking for 2 hours, and the audience was still there. We had about 125 people, the room spilling out, and nobody left. And he was talking to each individual as though he was talking to them personally, addressing them directly, but at the same time talking about the things that we were thinking about that time. Wisdom of crowds and crowdsourcing and all kinds of stuff that was hot 10 years ago. We don't talk so much about wisdom of crowds today. But my point is, our field is kind of funny because you start something 3 months ago and you kind of drop it, but then you go back 20 years and it was all done. You just read that paper. So for students from UCSD, just go read a paper from 1950, and you guys will be really hot after that. Okay. So I want to, there's a lot of keywords in my title, AI and machine learning and data science, et cetera. And actually, there's an article about people trying to, we're all data people, so we like to classify things. So how do you classify all of these topics? And I want to kind of lay the ground for what the audience I'm addressing and who will find what interesting. I've kept my slides with almost no mathematical equations to make sure that I kind of keep it light, but at the same time motivate you to think about how many of the techniques that people talk about today can be applied to what you're doing. So if I go too deep, kind of stop me. If I'm too shallow, just go back and read the book. Okay. So first there was statistics. In fact, the term data science, a lot of people claim credit for inventing the term data science and data scientist, was first introduced by a statistician back in 1974. And you can go back and read on Wikipedia. And came back again in 2001 by an environmental statistician. Till the computer scientists took and called it their own. That's kind of what we do. So statistics is a field that's been there for a while. And Alvarian at Google said, it's going to be the sexiest field for at least for the next 10 years. And it's proven to be, right? And so where do data scientists fall? So we have data science as a field was introduced formally now. A lot of colleges are offering master's degrees, affiliate degrees, et cetera, in data science. And it requires you to have a good foundation in statistics and other skills. So other skill is basically how to make it practical. There's a difference between looking at the statistics of data and actually making it work in a product. So if you look at a lot of companies, you'll see that data scientists belong in the product management organization, which is kind of weird. But the reason for that is you really need to take a customer problem or a product problem and translate it to science and apply it, and then take it back and apply it to the product. So that's why data science is kind of statistics and more. Then there is AI, which is a new field. A lot of it is statistics, but at the same time, and some of it is data science. And then we talk about AI, ML, and deep learning in the same thing. But ML is a subset of AI. So AI is about making computers smart, do automatic algorithms. Machine learning is a set of algorithms, and deep learning is even a smaller subset of it. But you need to know a bunch of other things like linear algebra and optimization, et cetera, et cetera. So basically, it's a big spaghetti, right? It's a bunch of things that you need to know if you want to be successful in this field. So where did I start? I started in none of this. I was a math graduate, but at the same time, very quickly I switched to doing what was exciting to do at the time I was graduating, and that is programming languages. I loved programming languages. A lot of my training was in programming languages. And there were people doing AI at that time, and I thought it was kind of silly and stupid because they would mostly make, recognize a dog or recognize a cat. And I said, it's useless stuff. And if you did compilers, you were a real computer scientist. And today, I rarely meet a student who's actually doing any compiler work, which is kind of very strange. And I was trained to think of programs as trees. So my mentor said, compilers basically are all tree transformations. An input program, which is a tree, and an output program, which is also a tree. I have to tell you a story about my first project as an intern. So I was back in India. At that time, there was a big US company, and they had a language which looked like modular. And they wanted to translate all of the modular code to C code. So where would they go? They would go to India, because they can get hundreds of engineers who will basically take the programs and then type it up. And the work will get done. And if you want it done in 5 years, you can employ 10 engineers for 5 years. If you want it done in 1 year, you can employ 50 engineers for 1 year, and you'll get it done. But that's kind of the formula that was applied, because mostly the labor was counted in terms of number of people required to translate code. So the company, they wrote a proposal for, I don't know, millions of dollars, said this is what it would cost per engineer per hour, da-da-da-da. And then I was an intern at that time, and I was trained by my mentor. He said, why would anybody manually, it is criminal to sit and manually translate code. So I've got a guy here who can actually write a program which can automatically translate all of your code. And he can do it in 4 weeks. It won't take 1 year, it won't take 10 years. It'll be done in 1 year, 4 weeks by one person. And I was unsuspecting, ignorant, and he called me and said, can you do it? I said, if you say so, yes, I can do it. So I was stupid enough to take up that task. It didn't take 4 weeks, it took about 2 months. And the whole idea there was to write rules, and it is fairly complex. The source language, if you go back and look at my publication, that was my first publication ever, how to translate code in one language into another language. So I kind of made a whole bunch of people unemployed by being the person who wrote that, the system that would automatically translate millions of lines of code. And the way the proposal was written was, there was a few $1,000s for development, and then for every line of code that was translated, the company would charge the client some money. So I must have got paid about equivalent of $100, but I learned a lot in that. But the whole point is, why write? So my boss used to say, or my mentor used to say, why write code when you can generate it? And that's the whole point of all what we are doing today. Again, it's something that was done before. And I never thought I would work on AI. And today what we're doing with AI is exactly that. We're trying to make it do things automatically. And so now, and from there, working on programming languages and compilers for years, I kind of went working on internet search engines. And even when I did search engines, I was kind of came back with this thing saying, I want to write as little code as possible. I want to generate code. So, and then I worked on, at IBM, I started with search and did a bunch of other stuff. And I worked at eBay for 10 years, where I did more commerce. But all the time, the whole point was write less code. And anytime anybody's bragging about writing a lot of code, probably they're doing something wrong. And finally, now, in my current job, I'm working with the compiler people. And I said, well, OK, I'm back to square one. I was about to retire. There's nothing else to do in computer science. There's this thing called AI, which I hated in the beginning. Now I'm combining that with what compilers do and say, hey, can we automatically do some things? So a lot of the formulas we apply have been seen before, but it's a new world, because there are other things that are available today that were not available before. For example, access to big data, ability to process big data, right? So I'll go through some of those things as we speak, okay? So why is that interesting? So let's look at the world of software development, right? So these are some statistics I want to provide. So I tell data scientists, spend about 80% of the time looking at data, and then remaining 15% proposing algorithms. So I have statisticians, I have data scientists, I have machine learning folks and AI folks in my team. And I tell them everybody has to spend time looking at data more than proposing algorithms first. Because usually what happens is the ML guys will come up with their algorithm. They've already have their bag of tricks. They won't even look at the data and say, let's apply co-clustering. Let's go and apply this other thing. Right? If you go back and look at the data, actually, you don't have to do very many complex things. Because the data will tell you what to do. Right? And you can cut it in ways where you can actually be pretty clever about the data. So anyway, coming back to this data, so there are about 17 million developers in the world, according to Tech Republic. And 2/3 of them are professionals, and the rest are hobbyists. And there are about 29 million IT professionals. And 20% of the software developers are from the US. And I'll tell you why I'm telling you this statistics here in a minute. Now, if you look at the top programming languages, Java, C, C++ are all, there are no surprises here. And the top IDEs over there. So basically, if you want to work on something that addresses a problem for a large community, if you want to do something good for a large community of people, there are 20 million customers for you. It's an interesting problem to work on. So I said, well, let's see what we can do here. Okay? So the nice thing about today's, the time we are in is that there's a ton of data everywhere. So one thing we did last year was we looked at 10 years worth of data from GitHub. So look at all the check-ins, all the code that has been pushed into GitHub a decade ago, since 2007, and see what do we see there. So there are about 10 million users on GitHub, about 26 million projects. About 62% of them are new projects, almost 400 million commits, 6.7 million committers, about 1 million active users every day, right? And 250K, about 250,000 new users coming in every month. And almost 750,000 new projects being forked every month. So the point there is that it's a very active platform. New things can happen. So if you ask me questions like, what's the new language? What are the languages trending? What are users doing? How are they coding? What are the design patterns for coding very much? I have everything buried in the data. If I can mine it in interesting ways, if I can mine it cleverly, and I can find the answers for the questions I have. What's important? What's a good software coding style? Who is doing what, etc. So that's basically what we're going to take advantage of as we go through this talk and this space. Okay? So there's a Forrester report which talks about how AI will improve the software development system, right? So if you look at the software development process, right? So first you got like an ideate, you analyze a plan, then you do a development, you got IDE, you write your code, your colleagues write code, then you look at each other's code and do code reviews, you check it in, you do a build, then you have a test system, so you go through the test process, and then you release it. And then release it, the customers report bugs, you get that data, you put it back into the features of your next release of your product, and you go on like that, right? So that's your software. And what this report says is at every step of doing this, there are opportunities for automation, opportunities for using AI. And we're going to go through some of the examples of how and what we can do there. Okay? And the whole point there is that if we use these as additional tools, we are going to disrupt the whole software development process. How software is being developed today. So if you work for a large company and you look at product releases, which they release every 2 years or 2.5 years, and a lot of this is because of the processes, how slow the processes are, how complicated the processes are. And as the software gets bigger and bigger, it's hard to test all parts of the software, do code reviews of all parts of the software. So you have to be very clever about what parts will be reviewed, and quite often the parts that get reviewed are the ones that are the least buggy, because you tend to conveniently review parts that are easiest to review. If you look at reviews, you have to write something for a review. It's almost like a paper review where you say things like, hey, write a nice comment, or change the variable name X. Don't you use X, you do something else. So a lot of them are mundane requests. If you have a complex code, very rarely you'll get a good comment on it. And the people who are capable of reviewing those are also fewer. So that's another thing that you see in this world, that because there are fewer people, the complex code tends to have bugs, and fewer reviewers who can review that code, they never get reviewed. And that's why we produce buggy software. So can we use techniques that in this world of AI to improve that process? That's the whole idea here. Okay? But it's different. Now, this space is very different from the space I was in before, which was the online consumer space, right? So if I'm doing like Amazon or eBay, their software is very different, where most of it is done. It becomes a web page, and the way it gets tested is you click on it, and if the page shows up, it passes the test, it's good, it goes on. And you can run massive number of experiments over there. So if you look at eBay or Amazon, about 95% of the site is being experimented on, and it's easy to run A/B experimentation. The user sessions are much shorter, right? User comes in, they search for things, they either buy or don't buy, they go away, they come back, they search. The sessions are much shorter. The experiences are much shorter. So even if you change the experience a little bit, you don't really lose your user. Whereas if you look at this space of developer space, there are lots of challenges. First of all, user experience is very different. You're all developers, so once you start an IDE, you're going to sit on it for a long time. You're not going to just change IDE by the day. You're engaged to it. And your development process is very long and complex. The way you use the product is very complex, right? And then when we collect data from you, we have to honor privacy. So if there is any telemetry data in a developer world, we need to be very careful about it, because it directly identifies you, right? And how do you experiment in such products? It's extremely hard to do. So there are lots of challenges if you're trying to use data science, and AI in the developer world. So let me talk about traditional compiler systems, traditional software engineering systems. So most compilers, all compilers, just focus on program structures. They look at programs as, like I said before, the programs are trees. So they look at them as mathematical objects. So if you look at compiler tools, or the testing systems, or the refactoring systems, et cetera, are basically based on formal proofs and verifications. So there is no data there. There are rules. There are, a program is a basically mathematical object, and the gods of compilers have said certain things that you have to do to the program to compile it, to optimize it, to check for errors, to test it, et cetera. You just follow it. And so tools are super conservative. So for example, if you look at a testing of a piece of software, most testing software will say, have you checked all the paths of the code that the code takes? So you write test software, even the automatic test softwares are like that. They check all parts of the code to test the software. Now the question is, if your code doesn't go through all the paths, or it doesn't go through most of the paths, why even bother to test it, right? So if data tells you that only 10% of your code is going to get executed, why bother about the remaining 90%, right? So this basically gives you a little bit of hint as to how you can use data to write a much cleverer testing software, right? Same with the optimization process. Like compilers work very, very hard to optimize your code. And there are rules on optimizing the code. For example, variable hoisting, or strength reduction, or interprocedure analysis, et cetera, et cetera. Compilers work very hard to optimize your code. But if there are parts of code that never get executed, why bother about it? So if I can provide you with data which tells you only certain parts of the code are getting executed, why not just work on those parts of the code and not bother about the remaining parts of the code? So these are just some very simple ideas what you can do. Okay? And same with code refactoring, right? So these are kind of the guidelines that typical, refactoring folks will tell you. What is a bad code? Bad code is code that is difficult to understand. So I've had colleagues, when C++ was hard, they would just say, oh, I wrote this really nice code, which had 7 levels of inheritance, and we even used multiple inheritance. And they bragged about it because they could write complex code in a language that allows you to do that. But is it really required or not? And you know that such code actually leads to more bugs, right? Or duplicate code, copy-paste code. We see in the internet world, if I see somebody's JavaScript, I copy-paste, I put it on my site, change the variable names, it's good. Right? Or even within a single application, nobody ever thinks of writing modular code in these scripting languages, right? It's all copy-paste code. And if one of them has bugs, you actually percolated the bug to all of them because it's copy-pasted and you lost the context, right? Poorly named variables, because that's another one. You can't read the code, you can't test it, you can't verify it, you can't review it. Often you see to do. This must be very familiar when you go through code. Oh, I need to go fix this. And it stays forever, it never leaves your code, right? Or sometimes you see documents when you go through the code, it says, oh, I don't know why it works, but it just works. So just don't touch it. And you'll see that even in production systems, right? So there's a lot of examples of bad engineering you see in software. And reviewers find it really painful. So the question is, can we automate the process of refactoring code in ways that these obvious ones can be gotten rid of so that the human beings can focus on something that's more complicated, right? So basically what I just talked about is you can use statistics in ML on this new source of data to derive patterns, right, and identify common cases. Once you identify the common cases, you can fix them, you can modify them, et cetera. And then you can combine data and metadata. So data here in this case, code is data, and metadata is behaviors, user behaviors. So how does, if you have a team of 4 engineers, right, somebody writes a lot of code, somebody reviews, somebody writes comments, somebody's a product lead, et cetera. And then annotations, which are the review annotations, right? Those combined with code will give you better handle on understanding the code. Now you can apply statistical methods to these and basically make recommendations instead of a simple rule-based system. So traditional software is all rule-based system. You can use statistical methods to do things in a data-driven way. Okay? So if you go back to code, Don Knuth, back in 1971, was probably the first data scientist in analyzing code. So one of the things he did was he went through about 800 Fortran programs and tried to study the code. All he did was ran standard compiler processes and tried to see what the code contained. And he found that 95% of the loops had an increment of index by 1. Right? 85% of the loops had 5 statements or less. And 53% of the loops were singly nested. So if you were to design a language, right, that satisfies 95% of your users, 95% of your loops are incremental by 1, you could come up with a construct which is much more compact than doing for I equal to 0, I less than or equal to n, I plus plus, blah, blah, blah. You could come up with a much nicer construct. You could test these programs much better. You could write, you could hoist them much better, et cetera. And there's a recent analysis by Alamanis and others who looked at, it's a very different scale now, 25 million lines of code. And they found almost very similar structures as to what Don found back in 71. They found that 90% of the code have less than 15 lines, right? 90% of the loops don't have any nesting at all and have very simple control structures. And using that data, they've gone further, and they've created 50 loop idioms. What that means is that ways loops are used in software to do different things. So now they have created a classification system where loops have been grouped into different structures. Now you can apply compiler optimization. So if I see a loop of this kind, I do this. Or code reviewers can look at saying, oh, I got a loop of a certain kind, I need to look for certain patterns. Or if you have automatically bug patching system, they can use these classification identities to say what kind of patches to put on. So you can go a lot more than what you could do 30 years ago, only because you have so much more data, and you can do so much more analysis on that data and come up with methods to do that. Okay? So as I said, so benefits of such a study is that you can do data-driven frameworks, code refactoring, and you can design. Then the plus aspect of the language is that the next language that you design, you have an opportunity. What do programmers do? Right? If they write loops, most of the loops are of a certain kind. Maybe you can have a compact loop structure, right? And the program optimizers can be smart as well. Okay. So there is an initiative called Big Code, right? And Big Code is kind of like it's a place where you can do data science on code. The idea is, it's kind of the Kaggle for code. So they bring machine learning algorithms, programming language systems, and software engineering system to one place. And you have lots of examples of code. You can run challenges there. And there are big code repositories over which you can run your algorithms, et cetera. So you can, there are challenges for predicting program bugs, program behaviors, program synthesis, et cetera. So let's go into the details of how to take advantage of data and metadata. So coding is a social process. What that means is, it's written by human beings. So typically, when things are done by human beings, you'll see you'll see preferential attachment. What that means is, you'll see more and more of similar-looking things. So this is where kind of, if you've heard of, Pareto 80-20 rule. So 80% of the code will be kind of repetitive, very similar, right? Because it's a social process. I look at your code, and I use the same design patterns, et cetera, et cetera. So you can take that advantage. You'll also see that probably there are only 20% of the engineers are very good, and 80% of the people are good enough, right? So if you take a team of 10 people, 2 people do most of the engineering, and the rest of the people are just kind of filling up the group, supporting these people. And that's a huge advantage to having these patterns, because when you build algorithms on top of these, you can take the intelligence that's contained in this 20% and apply it to the remaining 80%. It's just kind of what we call the Robin Hood approach, which is take from the rich, give it to the poor, right? So behaviors that are exhibited by these people who are highly talented can be percolated to everybody else. Or you can also say, look at this saying, if I got a big piece of software, probably most of the bugs are contained in about 20% of the code, or small part of the code. So how do I get to that 20% very quickly and ignore the remaining 80%? So it helps you focus as well. Okay. So in order to understand code and the metadata that codes with, we can borrow a lot from other fields. So for example, there's a large body of work in natural language processing, right? Compiler people have done a lot of work like in abstract syntax trees. So you can take advantage of that, right? Design patterns for algorithms, and the more recent advances in deep learning. So if you can put all these together, and you can come up with algorithms that can do automatic code refactoring, automatic code beautification, a lot of the compiler tasks that are actually coded up, automatic testing, program synthesis, and simple program synthesis, and identifying code quality, identifying code trustability, et cetera. So that's the whole goal of this. How do we use AI techniques to make a lot of the mundane processes in software development automatic? Okay.
What are ASTs?
Abstract syntax trees. So people who are familiar with compilers would know this. Your parser will go through your code and build a giant tree. And it's an abstract syntax tree. It will be decorated with type of the variable, where it's defined, where it's used, and what operator there is, et cetera. So that's a tree. You can walk the tree, and you can do stuff. And that's what compilers do. Most of the time, they're walking the tree and doing something with it. And a compiler process is basically a series of walk-through Dodge trees of this kind.
And the rules you mentioned, is that like a grammar rules, like DNF grammar or YAC, or is that some other kind of rule?
No, when I say rules for compilers, it's more like conventions. So if you want to write a compiler system, so for example, if you're writing a compiler optimizer, there are certain series of steps you follow. First do this, then you do that, then you do that, and look for this and look for that. And these have been, exactly, over years of research, which were not data-driven. So, and most compilers do them, whether it's required or not. Right? So let's look at code. So what is code? Code is executable, right? So, and computers need to understand them. So codes have a rigid structure, because computers can do only so much, right? Whereas when we speak or when we write, we are kind of fairly loose about that. So NLP, and compilers, the programs have to be right or wrong, so you cannot be vague about them. So that's one of the challenges with code. right? And basically, the end goal is to achieve a mathematically backed result, right? So while you can arrive at the result in many ways by writing the code differently, right, each path is spelled out in the structure. So it's very explicit, very recipe-driven. That's kind of how you write code, right? So this allows you for reuse of code, and if you follow the same recipe for something else or part of a recipe for something else, you can do that. So it allows for refactoring, reuse, and transformation very nicely. So you can write a program to process another program and do other stuff. Now, text is a language grammar, but the languages, most languages are kind of loose, and the way text is written is even looser. So if you human beings read it, they understand it. Computers read it, they have to work much harder, and they don't understand everything that human beings understand from that, right? So part of it is left for interpretation. Now, if you look at a typical compiler system or a software engineering development system, right, where there is code that is checked in, there is metadata like reviews or comments written by either the engineer or by the people reviewing it, plus there are other behavioral things, right? Who wrote the code first? Who checked it in? Who fixed a bug? Right? There's a whole network of information of how engineers participate in a code development process, and that's critical as well. But we've got algorithms in network analysis to take advantage of that. So I can look at a network of engineers who are developing a software system, and I can automatically identify experts. I could just say, oh, this such and such a person is expert in network programming, such and such an person is an expert in thread development, thread programming, etc. And based on that, I can automatically assign reviewers to the people who are experts rather than randomly assigning. So I can do a lot of stuff with structures of this kind as well, right? So combining all of these three things gives us huge opportunities for and benefits for ML, right? So how do we model code, right? So we are, on the one hand, code is highly structured. On the other hand, we don't have algorithms. We're trying to understand this energy behind the code, not just process it and compile it and make it run, but we are trying to see what the code does. Where is it wrong? What is the spirit behind the code? What does the engineer think when they were writing the code? So we need to come up with models for representing this code. We're not trying to just write a compiler and run it. We're trying to understand what's behind the code. So simple models are tokenizer models. So these are basically lexical code generator models, which is like a code is kind of like English text. It's a bunch of tokens, right? So in ML or NLP, there are n-gram models. N-gram models are basically in keywords, right? So it's like search queries, et cetera. So you can use that. Or in neural networks, you have the sequence-to-sequence models. We'll talk about that in a little bit. Or LSTM, which is long short-term memory neural networks. Other neural models, right? So there are a lot of neural models you can apply to the code, right? Now, neural models are superior to n-gram models because n-grams, it just says this is you can look at a code and say, if I say for i equal to 1 to n, do whatever. It'll take for I equal to 1 to n. It'll just treat them as tokens, and there'll be no relation between them. So it's almost like text mining, right? If I read a bunch of words in an article, I might just be able to say what words occur frequently, et cetera, et cetera. So there isn't much to it. Right? But on the other hand, they're very simple to process, or it doesn't take a lot of work to process them. But the neural models they perform much better, right? Because they kind of try to model the brain, right? So which means if I have something that's declared way ahead and used much later, I can actually tie them up by using neural networks. So I can reason in a much better way about my programs than I could do with n-gram model, right? So they can catch patterns that are cross-context, unlike the n-gram model. You can understand the sentiments in the code. Okay? The second kind of model is what I talked about before, is abstract syntax trees. So these are kind of representational models. So these are code-generating models that generate trees based on parts of trees generated so far. So you take a tree, then you kind of say, what does the tree contain? And then you generate code based from that tree, right? So these are better representation than sequence because now you've got nice structure. When I say A equals B, there's actually an equals operator, there's a left operand, there's a right operand, and I know what it is. But they're very, very hard to work with. The algorithms are much more complex, right? So there is some work. People have been using abstract syntax trees with Ellis Teams to do program synthesis. But it's still very early stages of doing that. And the third kind is kind of latent models. So latent models typically look for hidden design patterns, programming idioms, standardized APIs, et cetera, in the code. So we know the 23 gang of 4 work, 23 design patterns. Can we go through code and automatically identify these patterns? It's a hard thing to do, but at the same time, once you have a certain representation of them, you can do something magical with that, right? So people have used tree substitution grammars to represent these things, okay? And they also use graph-based representation for this. I won't go too much into detail. So let's talk a little bit about neural networks and code representation. So if you look at traditional neural networks, right, they are memoryless, meaning you've got many-stage neural network, but every stage you basically learn a bunch of things, and all you do is produce tokens at a higher level and then forget everything. And then the next layer learns from that higher level tokens. That's about it. There is no information carried from one stage to other, except for just changing the input data. Okay? Whereas if you go to RNNs, right, RNNs have loop, which basically means that they can carry information from one stage to another. They're basically, this is probably the only picture I have in my slides. So if you look at a module, there will be a loop back which says, okay, I'm going to carry this information, remember this. So RNNs have long memories, and they keep the memory around. But this is just unraveling the loop, and then basically it's a chain of modules that you can get. So there isn't much here as well, right? So we need a lot more than this. So what's next? So LSTMs are the hot thing today, right? People have been working on LSTMs for a while now, and they've been found to be very, very useful. So I'm going to make it simple here. What is a long shot? Does everybody know about LSTMs, or do I need to actually describe? So I suspect most people have heard of it, but don't know exactly how it works. So
you can always ask for show of hands.
Okay. A lot of people nodded no, so I'm assuming that not everybody knows about LSTMs. So basically what LSTMs do are long short-term memory systems. So they have long memory, but at the same time, they also have a forget node, which means they remember something, and then they forget when it changes state. So that's kind of what they're supposed to do. So I'm going to basically, the way they work is all written down here. So when LSTMs, RNNs block when you want to carry information from one place to another, right? They just pass information, but at the same time, they don't remember them. So by default, LSTMs have long memories, and they have chain-like structures, and basically chain-like modules that go through the network, right? And then in the module, basically what happens you can add or remove memory. So basically there's a forget step. So you can forget what you've learned before. So for example, if you're watching a movie and there's a certain character who had a villainous behavior, and halfway through the movie they turn into a saint. For the rest of the movie, they are saints, right? So if you miss that part of the movie and you come back and watch later and you wonder why that person is behaving that way, it's because you didn't see that part. So here in LSTMs, what you can do is that you can forget what the previous state was and replace it with a new value. And that's very important, right? So basically, it has a forget gate, then it's a store gate which replaces what we forget. Okay? And then finally, it outputs, it's a tanh function, which is with -1 and 1, which is where it gives you a result of, reduces it to the -1 to 1 space. So that's basically what LSTMs do. And there's another one. This is what you find in a lot of language translators. And I'll give you a couple of examples of this. It's called sequence-to-sequence model. So when you're translating, say, from English to French, or from common to code, or code to common, so they're like two different languages. So you can build sequence-to-sequence model, which can be built on top of standard language models by adding an encoder and a decoder step. Okay? So what happens in the encoder step is that the model converts the input string into some kind of a fixed representation. And in the decoder step, the model is trained to output sequences that are fixed representation from the encoder. So you always go through two sets of LSTMs. You first encode. So for example, if you're taking English, you take English and then translate it into a certain vector space. and then the decoder will take from the vector space and translate it to your target language. So that's kind of how things work. So I'm going to give you an example in a minute. So because you got Ellis Teams over there, if I see the word jaguar at some point, I want to know whether the jaguar refers to a car or the animal, right? So it carries the context forward, and the context says, oh, we are talking about cars or we're talking about automobiles, then it can say the jaguar is actually an automobile, it's a car, I'm not referring to an animal. Or if you're talking about zoos, then you can say the jaguar is actually referring to animals from the zoo. Okay? And there is another closely related one, which is attention-based network, where instead of looking at all of the data, you just focus on certain aspects of it, and you focus your attention on certain aspects of the model at every step. A certain aspect of the information at every step. So this gives you a much better performance. So I'll give you one simple example of how you can use Ellis Teams encoder-decoder model to build a bot. So everybody has heard of question answering system, right? So you go to a website, there's a bot there, the bot, you ask a bunch of questions to the bot, and the bot tries to answer. Traditionally, the way these bots were built they were built through a giant rule. So you have an FAQ system, and somebody sits and writes up questions and answers questions and answers questions and answers. And if you ask a certain question, the bot will say, oh, this was a corresponding answer, and it'll answer that question. If you ask a slightly different question, the bot won't be able to answer it. And that's why most of the time you go to AT&T or some other site. After 3 questions, you give up and pick up the phone and try to call somebody, right? And most of these bots don't work because they are hard-coded, tailored to answer only specific questions. So what the AI community has been doing is, this research has been going on for a while, but at the same time, we are starting to see good results. So suppose you have a large passage, right? In that passage, there's a bunch of information, right? And ideally, you want somebody to read the entire passage, and the questions they have might be buried somewhere in the document. But nobody's going to read pages and pages of documents to find out one answer to one question. So what people have been doing is going through these passages and automatically generating questions. And so when a user comes in and asks questions, the answer is found somewhere in the document, but they don't have to read the whole document. So for doing this, they train an Ellis Teams-based encoder-decoder model, right? So you got passages, you got questions, and you got answers. And what the system does is, so the encoder basically goes through the passages and produces a vector sequence representation for every answer in the context. So it'll go through the passage and say, what are all likely answers in the passage? And then it'll generate a question for that. Okay? And the decoder is basically another LSTM, which generates the questions from the answers, right? So I got an answer, now I need to generate a question from it. So it's translating the passage and the answers, and the context in the answer occurs to a question. By using this, it generates a giant question-answer database. Now when a user comes in and asks a question, it can answer the question by matching it with the answer that it has generated. Of course, there are a bunch of things that happen between these question answers and when the user comes in and asks a question. So for example, if you have a website and it says how to make tea, let's say. So there's a long recipe for making tea, and the user comes in and asks the question, how do I make tea? And suppose the system has found the question, how to make tea, and as an answer, it'll give you that answer. But if I say, can I make tea? The system may not understand that because the question was asked in a different way. So you need several other layers to go and map questions to some canonical space to say, okay, when the user asks a slightly different question, that matches to the other question that the user that's in the database. So there's a bunch of other work that happens when you try to build question answering system. Okay, and how do you train such systems? So today there's a big data set from Stanford called the SQuAD data set, which has got a bunch of passages, questions, and answers, and use that for training model. And you can build your system based upon that, and then you can apply transfer learning. So what it learns is, because all the text is in English, you know there's a certain structure to the sentences, right? From those, you can build those question structures and answer structures. Now you can apply the same model to your own data and transfer the learning from a different data set to your data set and try to build a system. Now, we are in the very, very early stages of this being successful. Actually, there's a challenge going on called the Squad Challenge, and they're trying to see how well the machine does compared to humans. And it's close enough, but not there yet. I don't know what the latest results are, but these are answering one-line, producing one-line answers, which means the question that it might ask might be a single sentence in the passage. And to answer, we're barely there. So now if you would, what I call a third grader comprehension. So in third grade English test, where you go to read a passage and there's a question and there will be a line somewhere in the middle and you got to highlight that line and that would be the answer. Just to do that, and that's kind of where we are. Now imagine writing a passage and trying to ask higher level questions of it, maybe an 8th grader level or a college level. That's very, very hard. We're not there yet at all. Okay? So sequence-to-sequence models have been found to be very useful for answering these kinds of questions. And a couple of other places you can apply to. So for example, you've got code and you've got reviews, or code and you've got comments. Now, if you want to automatically generate code, then you can use the code comment pair to kind of see, can I automatically generate code or not? What comment corresponds to what code, and what do I do with it? Okay? So what can these code models be applied for? So one of the things that can, obviously, recommenders. So when I say recommenders, most people think about people who bought this also bought that. It's kind of the classic example of a recommender system. So eBay and Amazon and all these companies, they model purchase behavior to derive intent, and then try to find the probability of your future use or intent or need to buy something. And they try to recommend you. And if they're right, if you buy, then the algorithms work well. If you don't buy, then they go and tweak the algorithms, right? So these intents can be represented in matrices, right? So basically, it's a large matrix of features, and then whether those features are yes or no, or you fill in the values of the features, right? And so recommendations are basically just matrix completion problems, right? So part of the matrix is not filled. By examples given in the parts that is filled, you try to fill the rest of the matrix that's not filled, okay? But on the other hand, in programming, deciphering intent is really, really hard, because there's programs mostly don't have any emotional energy, right? It's just code that you write to do a certain task. The intent behind is very hard to read, right? So, and as I said before, the good programmers write code differently than average programmers. So how do we take the energy behind what good programmers have done and apply it to what average programmers should be doing, right? Very similar to the recommendations that you see on commerce websites, right? So how does Amazon recommend you that, okay, you just bought a TV, you need a stand? Because they see that people who buy stuff, who buy stuff a lot, who buy things together, know better, and based upon that, they make recommendations to you. When you buy an SLR camera, a month later, they will recommend you a giant lens. They know when to recommend those, or when you buy a Roomba, they know that you need a battery, because the battery that comes with the Roomba is fairly useless. And the people who have done it before you, and they just copy that representation for you. And same here, right? So the practices that are followed by good engineers can be recommended to those that need it, right? The place where it has been used a lot is code completion. So code completion is where, I'm typing my code, and the editor predicts ahead. I don't know how many of you have used this feature. So, you write a function, you put a dot, you write a class name dot, and it tells you what the function you should be calling, right? And there have been several models that have been applied to this. If you look at traditional editors, what they do is you write a class name and do a dot, they'll give you an alphabetical list of things. There's a lot to be said for transparency, right? If every time I get alphabetical, at least it's consistent. But if I give you a machine learned model, right, and it's inconsistent, then it kind of disrupts programmer experience, right? So especially in software development, where it's a long process, unlike going to a website and buying something. You have to be very careful when we deploy these systems, because if you lose your engineer, the whole point of doing these things is to improve productivity of engineers, right? So you cannot, even though you might have a very nice model, if you don't present it very well, you might lose them, or you might make them less productive. So how do you evaluate the goodness of this? So if you go to Amazon and they recommend something, how do they evaluate the goodness of their algorithms? Do people buy more? Are people coming back more, et cetera? Those might be the model. And in the case of software, we look for things like, how many keystrokes were saved? If you have to type A dot B, that's like 3 keystroke, but if I type A dot and some recommendation is made to me, I reduce the keystroke, right? Or overall productivity. Are people writing less code and building more software? Are people reusing software more? So there are all these metrics. Are there fewer number of bugs? So all these things are metrics that you look for when you make such recommendations. Okay. The other area where there's a lot of automation that's going on is inferring coding conventions. So back when I was learning programming, I started with C, and it used to be, you used to use Johnson's style of coding or Ritchie's style of coding, where the braces go on the right or the bottom, et cetera, et cetera. So we were told how to write code. You can infer all of that automatically from looking at good software that's written. How to format code. What are the conventions we followed? Well, naming variables. So software systems, Alamanis and others, have built software systems that can go through code and say, hey, this is a better way to rename variables rather than A, B, C, et cetera, right? People write linter rules, but can we automatically generate linter rules based upon good software? So there is a ton of work that's going on in this area. Another area is inferring bugs, okay? So buggy code identification is kind of like anomaly detection. So there are rarer patterns. Very much like anomalies are rarer events, right? So the security attack to your site is rarer. It doesn't happen every day. So to detect these patterns, so we can borrow a lot from the way anomaly detection systems were built. And basically, these are things that happen in the code or patterns that you see in the code, which are much rarer than normal code, okay? So there's find bugs. If you've used it, it's got uses a language model to look at complexity measures. Also, you can use this to find syntax errors close to where this is one of the compiler challenges, where the error occurs. Okay. Now, the problem is because anomalies are rarer or problematic code is rare, right? You get a lot more false positives, and it's very hard to achieve high precision. Right? But it's okay, because then you put a human in the loop, and you kind of say, I'm going to flag X% of the code, even though only a part of it is going to be buggy. Right? So you can do that. Now, this is another idea that came about, I think, at least 20 years ago, right? The idea of literate programming. How many of you heard of literate programming? Nobody? Wow. So this also came from Don Knuth. It's a programming paradigm where basically you write code in a natural language with some little markup, and code will be automatically generated for you. So that was kind of the idea he had. So there's a whole bunch of things that came about it afterwards based upon that idea. Like web, no web was basically Knuth's inventions, but Swift editor in playgrounds, etc. But even if you look at Jupyter Notebook today, how many of you use Jupyter? A lot of people use Jupyter. It is supposed to be an environment where you can kind of combine comments with code in a natural way, even though most people don't do that. They use it like a scratch pad. But there are opportunities here in this place to actually make your code more literate, right? One of the things that that's another hot area in AI for related to programming is program generators and translators. So, which is basically program synthesis. Okay, so traditionally, how program generators work, like I explained at the beginning, they're a rule-based system, and tree pattern matching rules are written down, right? So the core language mechanisms are the same, and so writing the transformation rules are not difficult. You got a source language, you got a target language, and you got to basically write a tree pattern matching rule, right? And so the question here is, can ML help here? Even if we can produce approximate code, right? Can we do something here? So there's a ton of work that's going on in the program synthesis area. And the idea here is can we auto-generate programs from specifications? So if you have a large number of code and metadata associated with it, can you produce code that matches the metadata and reuse that code? Or can you teach a computer to write code through examples, right? So if you look at machine learning, how many of you have heard of AutoML? Anybody heard of AutoML? What AutoML is? So it's highly hyped. I'll tell you what it is and what it's made out to be. So here are some examples of automatically generating code. Anybody heard of SciGen? So folks at MIT wrote an automatic paper generator. So it's a piece of software they wrote, which basically goes and looks at a whole bunch of other papers and produce figures, produce tables, produce captions, produce references, bibliography, everything, and writes code. And they send these papers to different conferences and see if the paper gets accepted. And the paper gets accepted. They also found the quality of the conference to be really, really poor. And they got their paper accepted in a few conferences like that. It's a very clever idea. It was done a few years ago. Airbnb has something called sketch to code. Basically, you give enough examples of icons or modules for user interface, and it automatically generates JavaScript code or UI code for you. Right? There's another one that some startup companies making noise about. And everything is called AI today, but a lot of them are just very simple rule-based systems. Pix to code. So you give the image of a website, and it will automatically generate HTML for you based upon the image. So give it enough examples, it will figure out where the images are, where the image boundaries are, where the code section is, et cetera, and puts it all together and turns it into HTML. There is a program called Deep Coder from MSR UK and University of Cambridge, where they use what is called inductive program synthesis. And they're basically given a set of input and output and a set of programs. They search in that program space and find the program that will produce that output for that input. And so this is very useful in domain-specific languages. Now, these languages are very simple. They don't have, for example, for loop structures or conditionals, et cetera. They're very simple instruction-based languages. So why write code when you can automatically generate one based upon input and output? And they've used deep learning techniques to do that. MIT has a project called Prophet, which automatically finds patches for your code. So it's really interesting piece of work. And basically what they've found is that they've looked at a lot of data, and they found that across applications, right, code shares certain properties, which means it's kind of like Tolstoy said, right? Happy people are happy the same way, and unhappy people are unhappy differently. Here it basically says, code is, however different the software is, and the bugs that happen are likely to have similar patterns. So they go through different code. They went through a large repository of code and created a training set of human patches of how code was patched. And they built a probabilistic model on top of that. Okay? So what they looked at was original code, fixed code, and the code differences, and what bug was fixed, right? And whether the fix happened or not. So that's kind of a large repository of training data. They use that data to build a model. And now, given a new piece of code that's buggy, they could tell how that could be fixed. The program could tell how that could be fixed. And they found, basically, out of 69 defects, they could catch about 20 of them. So it's a pretty good automatic system, machine learning system they built looking at code and patches. So all it tells you is that once you have enough data, large amount of data, and you can identify a pattern, and you can fit into a machine that can understand it, model it, and work with it, you can actually do a lot of things automatically. And that's the beauty of these things. Yes?
The way you said, I can compose music. I have composed music using text, numbers, Excel spreadsheets, any pattern into music in any genre you want.
Yes.
Like the software coded.
Yes, so music in some sense is easy because it's highly mathematical, right? So there are patterns. So in some sense, you're actually going from a noisy space to a more structured space. The challenge here is going from a structured phase to a space which is noisy, right? It's the other way around. But yes, yeah. Finally, it is, you have to fit things into some kind of, yeah, exactly. Now, the second question will be, how enjoyable the music is, and how repetitive it is, and how does it compare to a Mozart or somebody else, right? Yes. But that's a good point, yeah. So the theme here is what people have been looking at is, beyond compiling, beyond understanding the structure of the code, beyond understanding the semantics of the code, right? What does this code do, right? What's the spirit behind this code, right? How does it interact with the neighboring code, right? Can we generate some specifications from the code? Why is it slow? Why is it crashing? These are high-level questions we face as engineers on a daily basis. Now, can we use neural networks and machine learning and AI to kind of extract that information from large amounts of data and from examples of human behavior, right? So somebody said this code is buggy because, or somebody said this is a fix for this particular part of the code. And if I see enough examples of these, can I build a machine that can automate that and give me, solve new examples of that, new cases of that coming up, right? So that's the whole idea of, because it takes a lot of data to train these machines. And today we have that amount of data available. So that's why all of this thing that was not possible 10, 20, 30 years ago is possible today. While the ideas existed then, there was no practical use case for it, or there's no way to do it. We worked with almost no data 20 years ago. Now there's so much data that it's almost impossible to think about doing something without data, right? So almost always I find myself asking the question, where is the data for this? Before you can even come up with something. Telemetry and data is kind of like the fundamental things that you do when you build any system today, right? And traditionally, we had experts for these, right? Today, machines can do that because of the large amount of data. And what we are doing is basically, we are pushing machine learning to its limit. I mean, not to its limit, but at the same time, we have the hardware that can process large amounts of data. We got large amounts of data, and we got the power to do that in reasonable amount of time. So we are doing more things through machines than actually making them manual. So the idea here is, how do we take mundane tasks that engineers have to do and automate them and make them a system? So the question is, you will read every other day. In fact, there's an article today about, are machines going to replace engineers? And two ideas, I kind of talked about in the beginning to now, and I want to just kind of bring it out, right? So everybody talks about AI. Nobody talks about IA. How many people know what IA is? I kind of put it up in the beginning of the slide. IA is intelligence augmentation, so which is kind of Douglas Engelbart's work, right? So AI is getting all the attention. I think of AI as more like it's a metaphor for anything that's automatic, right? It's not that machines are going to completely replace humans. So, both of these ideas were conceived back in the 50s, right? So there was the AI group and the IA group, IA set of people, or actually Douglas Engelbart, who said intelligence augmentation. The whole idea is IA is assistive. It is human in the loop. AI replaces human with a machine that will automatically do things for you, right? So it's a self-driving car versus an alarm system in your car that tells you that you're going to hit something or something is going to happen to you, right? So I think in a software development environment, IA is likely to be more successful than replacing something completely and deploying a software system, right? There are other scares about AI, right? So this was an article a few days ago from New York Post, right? Creepy Facebook bots talk to each other in secret language. You see more fake news once the word fake news got identified than real news, right? And then it's about Facebook canceling a project which was inventing machines that are going to be smarter than humans or whatever it was, right? Finally, it came to saying, no, Facebook chatbots won't take over the world. People from Facebook came back and said, no, there was no such project. Somebody made it up. It's not happening. So every other day, somebody wakes up and says, our machine's going to take over the world, and should we be careful? Should we be worried, et cetera, right? And there's a lot of things about AI generating itself, right? So that's where the question of meta-learning comes. There's an article I read about, you don't have to write AI code anymore. It will generate itself. There's another hype about, actually misstated. So the whole point there is, I don't think this idea is new, right? So anybody who has ever worked in a compiler system knows that once you have enough structure and patterns of a system, you can automatically generate it. That's basically the idea. So if you look at any machine learning model, any machine learning system, right? What do we typically deal with? You typically deal with preparing the data for a long amount of time, then modeling with that data, right? So you first do a lot of stats on the input, then you clean your data, right? Then you choose an appropriate algorithm. Then you tune the parameters, then you tune the hyperparameters, right? So these are kinds of, you do it over and over and over again, right? A lot of these tasks tend to be mundane, right? So for example, if you take the Netflix challenge, right? This data set is standard. The algorithms are slightly different from each other, and one is going to win over the other. So the whole point here is that if I get enough examples of positive and negative examples of a machine learning system that has worked and not worked, or the way I cut the parameters, the way I use the parameters, the statistical distribution of the data, etc. If I have enough examples of what worked and what did not work, the next time around I see a problem of that kind, I should be able to automatically put a program together that will work for me. And that's the whole idea behind energy behind this AutoML work. And it makes sense. It's not going to replace really good engineering or science you're going to do, but it's going to take the mundane things that you're going to do and make them automatic. That's the whole point of this. So today, if you use like scikit-learn, there's auto scikit-learn, which will do a lot of things automatically for you. Or Teapot is another example of a project, or AutoWeka if you use Weka for doing machine learning models. A lot of things will be automatically filled for you. One way to look at it is to say, oh, this is going to give me a model that will give me a reasonable performance. And then if I want to get a higher performance, I have to go and tweak it. So it'll give me the base code with which I can work, right? And you can apply it for transfer learning. So if I build a system which learns on one kind of data, I can take that and apply it to different data, and I get some performance, and I say, okay, why is it not working that well? It's working reasonably well, and then I tweak it to get a better performance. So there's a lot of goodness in this thing because of the way it looks at artificial intelligence in itself, right? So what other happens to data scientists next, right? So there's an article about, the data from LexisNexis back, I think 5 years ago said there'll be 240 exabytes of data by 2020. And a lot of these, many, many big opportunities for data scientists and machine learning, right? And it says by 2020, we'll need 2.72 million data scientists. This is from IBM, right? And McKinsey said we cannot hire enough data scientists and machine learning folks, so the demand is likely to exceed supply by 50%, right? So then what do? We create bots, right? We can create bots that generate machine learning code, right? So AutoML, Data Robot, Auto Scikit-learn, Teapot, all these things, which will automatically generate machine code. Now suddenly we are seeing articles which say data scientist jobs are at risk. 51% of them will be out of a job by 2025, according to Katie Nuggets, right? But the whole point is, I think we are going to enter a phase where the work we do is going to be more interesting, right? We're going to be doing more interesting work, and the mundane work is going to be done by the algorithms that we develop. So the robots that we developed are here to stay, and we are going to reach a higher level of intellect in the work we do. And frankly, I read this blog a few days ago, and I really liked it, right? Are AI models really a replacement for human beings, right? What is deep learning really doing? It's taking real-world data and turning them into some points in a vector space, and mostly doing geometric transformations, right? It takes a vector space and then takes points in a space and transforms it and transforms and transforms it, and produces some results which looks like something else we see on the other side. So if you look at the program, the AlphaGo program, it doesn't know that it's playing Go. It's just a program that manipulates some matrix, right, or tensor, right? Same with Deep Blue. All they're working with just mathematical objects, right? They don't know they're playing the game. There's no spirit to them. Actually, the example on the right is basically, the panda on the left. It's got a data distribution, and then what they did was they interspersed it with the Gibbon class gradient and combined it. The output data has exactly the same distribution. Now it identifies it as a gibbon, right? So, we shouldn't be too worried about it, machines taking over us, because, mostly they're doing mathematical work, right? They're not doing the intellectual work that we have. They barely have the intellect that human beings have, right? So really what it is doing is it takes real-world data, right? You take human experiences and kind of turn that into some kind of a mathematical function, right? You turn that into a bunch of constructs, and then you do a bunch of transformations on those concepts. And you give it some examples, but at the same time, all you're doing is transformations on top of it. And then you turn it back into saying, this is intelligence. It's not intelligence the way human beings are intelligent, right? So there's still a lot to be done, but at the same time, it's exciting that we are challenging ourselves with programs that we create that will challenge us, right? So that's a good thing. So why is it really exciting for us? So today, if you have these problems, access to data is not a challenge at all, right? There's tons of data available. You can put this, try this on your machine, and you can go to the cloud. And nice thing about clouds is that they provide you with a fail fast, scale fast method. So which means you try it. If it doesn't work, you throw it away. You don't have to do anything. If you have to scale it to millions of data points, gazillions of data points, the cloud will scale for you. So in some sense, it provides you with an environment where you can scale your algorithms with the amount of data you have. And it'll still work. You don't have to buy that much hardware. So if I was building a company back in 2000, I would have to first go and invest a bunch of money in hardware. Today, I just can go to a cloud. I can set it up. If 6 months later I get no customers, I can shut it down. Nobody will notice, right? I have not lost any money. But if customers come screaming through the doors, then obviously I can scale it and I can pay for it, right? There are many, many, many examples of it we see. Sometimes we don't even see the companies that fail. Almost everybody has a private cloud account where they're trying out something or the other. None of them see the light of day, right? So that's the beauty of the cloud. So it provides you the scale that you can deal with it without actually having to buy those machines. And the other nice thing that is happening is, a ton of AI tools are coming out of companies like, Microsoft and Amazon and Google. Many of them are free for you to actually go and try them out and play with. So the starting point for being a machine learning AI person is very, the bar is continue to be lowered, right? You don't have to know a lot of the concepts. You just have to know what they do, and there are tons of tools that you can use to develop AI software. So the space is still being defined and shaped, even the space of the tools on the cloud. But at the same time, the opportunities are huge, right? So I want to close with a few comments here. What we have learned, in my experience in the last couple of years, is open source gives us a ton of data, not only about software, not only about code, but also the engineers or the coders, the reviewers, the network, etc. So this is amazing amount of data, amazing quality of data that we have. Now we have cloud that allows us the opportunity to process a lot of these data, right? And with the recent advances in AI and ML, we are actually able to do things that we could not think about doing even 5 years ago, right? So we are bringing programming language and software engineering even closer to AI because of these things. And a lot of the software processes are likely to be automated and can be automated in an interesting way, right? Still, there are other challenges, like computer languages are still highly synthetic, right? They're not like natural languages. So, but they're programmed by humans, and that's what we are taking advantage of. Data sparsity is huge. What that means is, while you have a lot of programs, there are so many variations on these programs that you don't get enough examples of one kind. So there are a lot of these challenges we have to continue to solve, but at the same time, the opportunities are huge. Right? So with that, I'd like to close, and if there are any questions, happy to answer. Yes. The question is, Alexa being AI. So maybe I should ask the audience, how many of you think Alexa is AI? How many have done useful things with Alexa? Few people. So I got my first Alexa, I think last year, and it could do a few things. It'll play music for you. It'll, you can ask about the weather. You can also have a conversation with it, which will be humorous. I'm not sure if it's exactly useful. One of the uses of Alexa was to put things in my shopping cart. So that's a good example. Okay. So I have two boys. My second one, my older one is a vegetarian. My second one is a meat eater. So often he would want to put meat items into the shopping cart for the older one. So he would say, Alexa, put bacon for my brother. And I go back and look at my shopping cart. It'll say, bacon for my brother. So there'll be a whole bunch of things in the shopping cart that Amazon cannot ship, right? But it just puts in the shopping cart. So he was excited it was AI. It was putting in the shopping cart. I was doing all the work of removing things from the shopping cart, right? But the point is, Amazon is collecting a lot of data. If you go back and look at how Google did voice recognition, or if you look at Siri the earlier days, most of the conversation with Siri was, how many swear words it got, etc. But the point is, it doesn't matter where it is today, where it will be tomorrow. Today, it's collecting a lot of data. It knows where it goes wrong. It knows that some kid is putting a bunch of stuff onto the shopping cart, and the dad, or it doesn't have to know that it's a kid and a dad, is removing it from the shopping cart. It can also look at the data, what's going into the shopping cart. So it knows that it can improve over time, right? It's getting enough data to say, I'm doing this wrong, I'm doing this wrong, I'm doing this wrong, I'm doing that right, I'm doing that right. So it's getting positive and negative examples of doing things. And at huge scale, I don't know how many Alexa pods have been sold so far. So every time you interact with that device, you're giving Amazon a piece of data that's going to be useful for the next algorithm that they're going to build. And that's how these things get better. That's why I think I can't stress enough about availability and use of data over algorithms, right? Algorithms finally will be very simple, because if they figure out how to throw away data, that's good enough, right? All it needs to figure out is what not to put in the shopping cart, right? When not to put things in the shopping cart. And it'll happen. And I can see it happening, and so which means it will happen, because I can see what algorithms could be developed to do that, right? So a lot of these examples look trivial. Even the automatic program generators I talked about, they generate trivial, very small programs. But that's today. And it's only the beginning, right? So a lot more things are likely to be, the compute power is going to be much bigger. The data availability is going to be much bigger. The algorithms are going to get only smarter and better, right, as we see more examples. We barely scratched the surface of how artificial intelligence can be used to understand these things, right? Yeah. Okay, did I answer your question? Yes? Okay, I'm going to rephrase both of your questions. So the first question is, there was something about question answer generation, and your question was, how real is it, and can it go into products? And I think all of this at research level look like, blue sky problems, right? They seem like, yes, there is a program to automatically understand every passage you write. But when you put it in practical context, right, there are contexts where many of these things can be done, right? So for example, if I want to have very simple questions, again, you to go back to the way I was saying, stupid things can be done by machines, and you don't need human beings for that. And there are a lot of stupid things that happen in every system. And you want to automate those parts. And even if these programs are able to do that, that's highly valuable. So when I deliberately said a third grader comprehension. Third grader comprehension that's useful. That's useful, right? Because otherwise it's a human being sitting behind the phone and saying, hello, how can I help you? And you ask an obvious question, they give you an obvious answer, right? But at the same time, it's not there anywhere on the website, and you have to go and pour through a bunch of things to do that, right? So is it going to answer all the questions you have? No. So let the machine answer the stupid questions, and the complicated ones human beings will answer, right? That's why I kind of push for IA. And the second question was, is there a limit to the data? I think if you have worked with a lot of data, one thing you will realize is you need a lot of data, and you also know how to very quickly throw away data that's not useful. So it's a clever use of data. So that's why, if you look at data science, I say data science is 90% data and 10% science. You spend a lot of time massaging the data, right? More data is good, but at the same time, more data is not necessary. Just blindly adding more data is not very useful. You have to figure out how to cut and how to throw away data that's not useful. So very quickly index the data in ways that can be useful to you, right? So for example, if I'm building a search engine, is 20-year-old data useful to me? So we used to, at eBay, I was building one of these systems I called the infinite store, which means anything that was ever bought or sold should be indexed, right? So you would think of it as infinite data, right? Because if you go back to 1996 or whenever, you're looking at billions and billions of data points. But at the same time, how do you store it? It's very different. And another thing you see is when you have a large of data, especially this is, again, I gave you the example of preferential attachment, right? You see a lot of repetition, a lot of things that are similar to each other. So you have ways of cutting the data in ways that you can combine them and compress them in very intelligent ways. And that's another skill that you pick up as you work with more and more and more data. Yeah. Is there some other question? Yes? Yeah. So the question was, what about Google's automatic machine learning system? So I don't know, I've not seen the press release, but at the same time, the paradigm makes sense, right? When you're doing a repetitive task of training models, collecting data, creating features, selecting features, building models, deploying them, getting positive and negative examples, for a similar class of problems, right? You're doing it over and over and over again. And computers are very good at taking things that are repetitive and automating them. And that's what they're basically talking about. If think about, here's an example I can give. Suppose there are 100 chimps, each one in a cage. Each of the cages have tools, and the chimps have to escape. Okay, there's a bunch of tools there. The chimps have to figure out what tools to use and how to escape. So the first chimp is trying out a bunch of tools. All the other chimps are watching this chimp, and eventually it escapes, right? The second chimp says, okay, I learned something from the first chimp. It tries some other tools. It may escape, it may not escape. The third chimp is looking at the first and the second chimp, right? So it's going to be slightly smarter than the first and the second one. Or at least when you go to the 100th chimp, the 100th chimp is going to do very little work because it has seen enough positive and negative examples of, now if you think of the tools as features, right? How are the features used? What features were used? What worked? What did not work? Once you have enough examples of that, for the 100th chimp, the task is fairly easy. Now I can complicate it by saying, well, each chimp was given different tools, or the challenge was different. The lock was in a different place. The cages were of different size. They were made of different material. Now I'm complicating the problem. But at the same time, for the mundane problems, right, if I see enough examples of it, the N+1 solution is fairly straightforward, right? They talk about democratizing machine learning. All they're talking about mainly is things that are done over and over and over again can be automated, can be done automated. Sometimes if you look at, even go back some years into MapReduce, right? MapReduce is a fairly straightforward concept. But they democratized it because suddenly we are in a space where there's a lot of data. I used to do scientific computing before, and this is 101 for scientific computing people. You take a lot of data, and process them parallelly and reduce them using a reduce operator, right? But at the same time, it was meant for the scientific community. Now suddenly all of us have access to data. All of us have access to text data, internet data, water image data, all kinds of stuff. We need to process them at scale, right? And there's a design pattern they offered us and code that goes with it that most of us found useful. So suddenly they kind of democratized distributed computing. So it got all of us to the next level of doing large-scale computing or large-scale engineering. And that's the beauty of it. So suddenly, you will have tools, or you have tools today, right? The announcement is it's marketing, but you have tools today that takes you to the next level of doing machine learning for mundane things, right? For things that you do on an everyday basis. The problems you solve every day, you can do them differently because of these tools being available. Okay? Yes. So the question was, can ML help me draw my UML diagrams? Is that correct, what you're saying? Is that a good summary of your question?
In a nutshell, yeah.
In a nutshell, okay. Can ML, if you have enough examples, right, of humans having done it in some particular way, and you can break it down into some mathematical model, yes, you can do it. So the example from Airbnb about taking the design patterns or icons or images or sketches that UX designers have done and automatically generating HTMLs. Basically, they gave the machine enough examples of how to draw or how to create a certain functional button on the web, a functional object on the web. And so that if you give it an examples, it can create the N+1 on its own. If give an examples with certain use, then it will create the N+1 with a slightly different use. So the same with automatically generating UML probably can be done. I don't think it's rocket science, as long as you have enough use cases of it, as long as you have enough positive and negative examples of it. Yeah.
So thank you very much. We appreciate your talk.